Hello, I am Gihan Marasingha and I'm a lecturer here at the University of Exeter. And today we're going to talk about a little mathematical puzzle that actually has lots of applications in the real world. So what we have here is a little 8x8 grid. And 8 times 8, as you well know, is 64. We've also got these dominoes. We've got 32 dominoes. And what you'll notice, cunningly, is that each domino covers exactly 2 squares. So the question is, can I tile my 8x8 grid with dominoes? Actually, that's a really easy problem. Yeah, clearly you can. Look at that. I mean, I've got 4 dominoes in the first row. I've got another 4 dominoes in the second row. No problem. Yeah, I can definitely tile this 8x8 grid with dominoes. But now let's imagine we've mutilated our little grid. If we take away the 2 diagonally opposite corners, can we cover what remains with dominoes? So numerically, it seems as though, yeah, that shouldn't be a problem. I mean, we had 64 squares originally. We've taken away 2, so we've got 32 squares, and that's an even number. So definitely, numerically, it should be possible. I mean, if I took away just 1 square, numerically, it wouldn't be possible because I've got 63, which is not even, so I can't cover it with dominoes. So have a go, see if you can do it, and see what happens. And I'm going to guarantee that you won't be able to do it. You won't be able to cover this mutilated grid with dominoes. And how do I know this? Well, I know it because of maths. So I'm going to put that to the side for the moment, and I'm going to get another 8x8 grid. And this 8x8 grid, of course, is a chessboard. It's the same thing, it's the same grid, but we've got extra information here that wasn't evident in the original diagram. I mean, it was there, but it was hidden. We got the extra information that we can color the chessboard with squares of alternating colors. So we've got black, white, black, white. Now let's imagine putting down our dominoes. And what you notice immediately is that when I put down a domino, the domino covers squares of different colors. Right, so I put down this domino, I've got it coloring a black square and a white square. This covers a black square and a white square, and so on. So if I've got my 31 dominoes that are meant to cover the mutilated chessboard, well, I'm going to have covered 31 white squares and 31 black squares. So yeah, I mean, that makes sense. I've got to cover 31 white squares and 31 black squares. But with the mutilated chessboard, how many white squares are there? Originally, there were 32 white squares, and I've taken away 2 squares of the same color. So I've got 30 white squares. And that tells me it's impossible to cover it with dominoes because I can only cover it if I had 31 white squares, and I have 30. Not possible. Okay, so what we've proved here, in fact, if we generalize, is a necessary condition for being able to tile a mutilated chessboard. If I take away any 2 squares of the same color, it's not going to be possible. So if I took away these 2 squares, which are both white, or these 2 squares, which are both black, then by the same reasoning, it's impossible to cover the mutilated chessboard with dominoes. Well, that's nice. That's a nice bit of clever mathematics. But mathematics isn't just about saying, okay, that's a puzzle, and we've solved the puzzle. It's also about saying, well, what other questions can we ask? We've solved this necessary condition problem, but is it a sufficient condition? That is, if I now take away 2 squares of different colors, say this black square and this white square, can I tile the chessboard with dominoes? So maybe have a go. Take away 2 particular squares and see if you can tile your chessboard with dominoes. And what you'll find, I'm going to argue, is that you can. Okay, I mean, hopefully you can. I mean, it certainly is possible, and I'll show you how you can do it. So I'm going to throw away this chessboard and get another chessboard, a paper chessboard. And the reason it's paper is because I'm going to draw on it, and I don't want to mess up the beautiful chessboard that we had over there. So what I'm going to do is I'm going to draw a path on the chessboard that goes through each square exactly once. Okay, so, and that's certainly possible. So we'll just kind of sneak around like this. Sneaky, sneaky, sneaky. So we're sneaking around. And yeah, brilliant. We've got this path that goes through each square exactly once and it returns to itself. In fact, this is called a Hamiltonian cycle in the topic of graph theory. Now what I'm going to do is I'm going to take away two squares of opposite colours. And it doesn't really matter which ones I take away. Let's just take away, for example, this black square. So we've taken that away. And we'll take away some white square, let's say this one. So we've taken that away. So we've dissected the path into two new paths. And let's follow along the new paths. So let's start with this path. It starts on a black square. We wend our way through the Hamiltonian cycle, or what was a Hamiltonian cycle. And we end up on a white square, right? So we started on a black square and we've ended up on a white square. And that means, of course, that we can cover it with dominoes because we've got the same number of black squares and white squares on this path. Okay, I won't do the whole path, but I'm sure you can see that that works. And likewise, if I start on this path, which starts on a white square, I wend my way through and it ends up on a black square. And since this is a fairly short path, I will actually do it. So here we are. We're covering that path with dominoes. And there we are. So it's definitely doable. Well, that's great, that's fun. So what's the practical application of this bit of mathematics? Well, as I said, understanding these kinds of things is part of the branch of mathematics known as graph theory. So how is graph theory used in practice? For example, let's look at Facebook. In Facebook, there's what's called the social graph. So this is the connected graph of all of the people who are friends with each other. And then you've got other disconnected bits of people who aren't friends with each other. And Facebook uses the social graph to help you connect with your friends and to send you advertising, that kind of thing. How else is graph theory used? Let's suppose you're planning a trip, let's say from Scarborough to Exeter, and you go on Google Maps or some other map application. Well, Google Maps will have a graph of the UK road network, and it will use clever graph algorithms to figure out the optimal route from Scarborough to Exeter. So we've seen a bit of a mathematical puzzle, and we've seen how it applies to real-world applications. I hope you enjoyed it.